So welcome back. We are now, yeah, I say that a lot. We are now in the second part of the lecture. It's called Lessons Learned. Why? Because that's all things that have been done 40 or 50 years ago. And even though big data is new, a lot of things are not new because we have to learn from what people did before. Learning what people have done in the past is an enormous accelerator for building things because you don't remake the mistakes that they have already done. So this is why we are going to take the time to go through the early databases. Now, I have to give you a word of warning because I want to make sure that you don't panic. So two things are going to happen in this lecture. Some of you will be bored today and tomorrow. They will be bored because you've already seen that in the database lecture in your bachelor's, right? Take it as a brush up. It's just a refresher of things that you already know, but it brings it back to your mind. Some other people will be scared at the end of today and tomorrow's lecture. And I want to tell you, do not be scared. Because the reason you're scared is that I'm going to dump at you a whole semester of material of relational databases, and that's very scary because normally we don't take 2 hours to do it. We actually take maybe 28 hours through an entire semester. But the reason you shouldn't panic, and it's really not a big deal, is that you actually don't need to know all of the details for the big data lecture. It's relatively independent of the rest, but I take it as a survey. So just sit back, look, get the main ideas of what was done in the relational databases. The main assignment that you have will be to learn SQL, if you don't already know SQL. And SQL is really not difficult to learn, right? Business people learn SQL. You don't need to be a computer scientist. So I love business people. I mean, you cannot fund startups without them, right? So you need everybody in the ecosystem. What I want to say is you do not need to be a computer scientist to learn SQL, right? So I recommend that that you take the time in the exercises. Next week, you will have a few Jupyter notebooks to practice. All right, who is ready? Who is going to be bored? Who is going to be scared? Okay, most men, if I'm happy, if nobody is bored or scared, then this is good. Okay. This is Edgar Code. Edgar Code is considered the father of modern relational databases because he had the genius idea of separating between tables and manipulating tables and all the complexity of the implementation that nobody wants to care about. This has a name. It's called data independence. Data independence is the idea that whoever uses SQL and interacts with database management system, so the whole word is Relational Database Management System, RDBMS, if you see it somewhere. So you just look at a table and interact with a table. It feels like interactive with a spreadsheet software like Excel, right? So that's a lot of people understand this. The physical storage, you don't need to see it. That's all hidden. It's implemented in C++ or Java or whatever. You don't need to care about this because all you see is that. This is called data independence. It means that you can implement exactly the same thing on top of a C++ local implementation or a clay tablet. Yes, absolutely, you can do it. It's going to be slower, but it also works. You can also implement it on top of spreadsheet software in such a way, a single hard drive or a cluster of machines, and still get exactly the same look and feel for the system. That's the magic of data independence. So remember that data independence, that's absolutely fundamental. It's this idea of separating the logical layer from the physical layer. You can even do it on DNA. People did it. This principle of data independence will actually follow us throughout the semester. It's true for relational database management systems. It's going to be true almost at every level of the stack. When we build something, there will be an upper part and a lower part, and the upper part will be the logical implemented on top of the physical layer, right? And you can do it even with many more layers than two, right? It's something quite natural to do for a computer scientist, actually, to reason and abstract in this way, right? So this is data independence. Then we saw data shapes already. So I told you that there are these 5 fundamental shapes, right? So trees, tables, cubes, graphs, and unstructured text from which maybe vector databases will spin off at some point. Today, we'll focus on this, right? The brush up on tables. We'll have plenty of time throughout the semester to explore this, and this we explored in information retrieval. Okay, so I'm focusing on the tables. And don't worry, because people did it 4,000 years ago. That's something very natural to look at. So the general idea for tables, and we'll see it's also true for all the other shapes, if I oversimplify everything, we basically have a layer of storage that we store it in bits. Then we have a layer of compute, like CPUs and so on. Then we have a layer of modeling. This is describing what a table is. And then we have a layer of language that is basically a query language like SQL. You could put an LLM also on top. That's probably going to happen at some point. But this is the idea of these four layers. Right? So let's focus on the model, because this is basically, as you might have guessed, this is where data independence comes into play. Right? You basically do the cut here. This is the logical part. This is the physical part. So when you define a model, like the relational model, as it is called for relational tables, you need two components. You first need to say what data looks like. You need to describe a table. And you need to say what you can do with that data. So the manipulation primitives that you can apply to that data. You will see it's actually pure math. In fact, you can do an analogy with cooking. You can define what food looks like. So all the ingredients, something that can be eaten. And what you can do with it, that's all the verbs that you will find in recipes, right? You can mix, pour, break, dry, bake, grill, melt, mince, mix, and so on. We'll see that it's the same thing for tables. We'll describe tables. The words we'll use will be project, select, group, sort, and so on. We will also have the verbs that we can apply to it. Okay, so now, again, now I keep repeating the same thing, but it's very important. How does data independence work? It works because back in the 70s, putting myself here, yep, here. Back in the 70s, this is what we had. You have a single computer, a single hard drive, single CPU. Back then, we didn't have all the multiple cores. And you implement a relational table with SQL on top. What do we do now? What did we do maybe 10 or 20 years ago? We kept exactly the first two layers as they are, but we swapped the two bottom layers with the data center. We didn't change anything there. Plus, we did the same for cubes, for trees, for graphs, and so on. That's the beauty of data independence. You can change the physical layer, but without actually changing the logical layer. You might still notice a change from the logical layer. What you might notice is that it's suddenly faster. That's what you might notice. And you think, okay, maybe somebody did an improvement on the physical layer, but the behavior should be exactly the same. In fact, this is what we do in big data, as you might have guessed, that site. But in the bachelor's, you basically study this architecture. All right. So then let's start describing what a table is. That you don't need to worry about. I could do it in a primary school to third graders, what I'm about to say. What is a table? Well, it's something that looks like this, right here, right? Now, there's plenty of ways you can call it. You can call it a table, but you can also call it a collection, a relation, a relational tables. These are just synonyms, right, that you might find in the literature. We'll just call it a table, typically. Collection, you might find a lot in a big data context that you consider a table to be a collection. All right? So this is a table, looks like this. Now, another concept that belongs to the relational model is the concept of a row. A row, something like this, right? Horizontal, that's made of multiple values, like this. Some people call it business object, item, entity, document, record, tuple. The business people call it business objects. I actually heard that a lot in company environments. Records is also very often encountered. A document, we'll see why it's also called a document when you denormalize the data. An entity in the entity relationship model. A tuple could also be called a tuple, we'll see why. But these are all meaning the same thing. This is here a record or a row. Okay. Then we have a column like this. A column is also called an attribute, a field, a property, a key. Be careful if you call it key, that's in the context of JSON, but not to be confused with primary keys. Come to that. Attribute and column maybe are the ones we should call in a relational model context, right? So this is the column. So the row and the column. And the intersection of a row and of a column gives you a cell. And we'll talk more about the content of the cell a little bit later. What's also important, and I'll come back to that, is that if you look at a single column, the values in there tend to be of the same type, right? I'll tell you more about that. So table, row, column. Some of the columns might be a bit special. It can be 1, it can be 2. It can be special because it identifies the records. Imagine you store people in a table and you have a column that is the social security number, the AHFAO number. Let's say you're the tax office, right? You're the tax office, you have the list of everybody who fills the tax return, you have the list. The social security number is a special column because it's different for every record. That means that if I give you the social security number, you know the records. That's called a primary key, right? Who heard of them? You studied relational databases? Awesome. Who never heard of a primary key? Everybody heard of a primary key? Wow. If you didn't, so really think of the social security number, the AHFAO number in Switzerland. Some people call it a row ID in the context of NoSQL, a name, also a key, sometimes secondary key, but we'll see it later. Primary key is really the main one. If you go to real systems, it's very often that the primary key has a single column with a letter ID. Like the ID could be person ID. If it's, let's say it's a list of computers, then it's going to be CID, computer ID. So this is kind of a common practice if you lack imagination and you just want to make up some name for the column here, right? Okay, it's quite simple actually, right? We have a table, we have rows, we have columns, we have some of the columns that are special. By the way, it can be several, doesn't have to be just one. Imagine, for example, the number plates, the license plates on the cars. In Switzerland, you need 2 columns. You need the canton plus the number. That would be 2 columns that together identify a car. Okay, and finally, yes, the intersection of a row and column is a cell or a value or a scalar. It's the same term that we use, for example, for vector spaces when you have a simple real number as opposed to a vector. So a scalar, a characteristic, a fact, that's when you do data cubes that you tend to do this. But let's just say a cell or a value that is in there, right? So this is it. This is table, row, column, primary key, and value. So at first, it looks easy and intuitive. What's incredible is that when you start applying the math, defining it mathematically, you can actually build a beautiful theory called database design theory that you can teach across several weeks in a semester. It looks very, very simple, but actually you can derive a lot of incredibly complex and useful things out of something that simple. So that's the model, right? The second part of the model is what you can do with tables. And now we have a very fancy name. It's called an algebra. It's an algebra, just like you can take numbers and add them and multiply them, and you can take in a vector space, the scalar products and so on. Well, you can do the same with tables. You can take tables and you can apply things to them. You can transform a table into another table and so on. That's called the relational algebra. Who remembers the Greek letters? Sigma, gamma, what's all? Wow, okay. So before we get to that, let me explain why it's called relational table. It's actually called that way because one of the ways you can define a table that's very common in textbooks is as a mathematical relation. Who knows what a mathematical relation is? Who forgot what it is? Okay. Formally, it's technically a subset of the Cartesian products, right? Basically, what you do is you define a domain, a set that has all the possible values you can have here, another domain that has all the possible values you can have here, and another domain that has all the possible values that you can have here. When you do that, and you look at a single record, a single row, and you think of it, what is it mathematically? Well, mathematically, it's a tuple. Why is it a tuple? Because if you think of it, it's one value taken from that domain, one value taken from that domain, one value taken from the third domain. That is called a tuple in mathematics. And a relation is a set of tuples, right? If the tuple is in the set, then the relation exists. If it's not in the set, then it's false. You can also view it like a predicate. So if you do the math and consider that a relation is a subset of the Cartesian product, it's just a set of tuples, but of course, you are not going to view them like this. You're going to display them like that, okay? Takes a bit of thinking actually to understand the mapping between tuples and tables. Who does see that? Okay, who doesn't? Okay, even if you don't have to worry too much because this is the definition that you find in textbooks. I don't like this definition. The reason I don't like it is because it has a few limitations. It seems to do the job at first, but one of the things, for example, that it doesn't do is that when you define a mathematical relation, there is an order between the sets. That's the first value, that's the second value, that's the third value, right? So there is really a first column, a second column, a third column, mathematically. But in a relational database management systems, normally the order of the columns doesn't matter. If you swap the columns, they all have a name. If you swap, for example, the first name and the last name, and you put the last name before the first name, it's still the same data. It doesn't change the semantics of the data. So this is why mathematically it has a few limitations, but still it gives you the origin of the why it's called relational database management systems and why it's called a relational table. There's a simpler definition that I actually prefer to use in the context of big data. And another reason I like to use this one, as we will see, is that it naturally leads to big data, more naturally than this one. So how do we define now a relational table? It's like this. First thing you need is, it's called a schema. It's a set of attributes, right? Here you say, okay, I have 4 columns, PID, last, first, and country. And then you define that part, it's called an extension, that's the contents of the table, and it's going to be a set of tuples. Here it's a set of 6 tuples. There's the tuple 1 Einstein Albert CH that basically populates the attributes. This says the PID is 1, the last is Einstein, first is Albert, and country is CH, right? Do you agree this is a set of 6 tuples? Who agrees? Okay, great. Now, there is a bit of freedom in whether we call it a set or a list or a bag. And that really depends. There's many ways to do it. It depends if the order matters. Do you consider that the order of the records is important? Then you should take it as a list of tuples. Then there's a first tuple, a second tuple, and so on. If you don't care about the order at all and you don't have duplicates, that's just a set of tuples. If you shuffle the records here, it doesn't matter. Imagine you're the tax office and you shuffle the table that has the people filing their taxes. Nobody will see the difference, right? It's just the same data. So there is a bit of freedom in order to say a table is a set of tuples, a bag of tuple, or a list of tuple. What is a bag? Who knows what a bag is? Yes? Exactly. Yeah. So the bag is like a list because it's like a list because it can have duplicates, but it's also like a set because it's not sorted. So it's midway, intermediate between set and list. If you were in information retrieval, you already remember that, right? You already know that. Okay. The original relational model is a set of tuples. In the original version, it was defined as a set of tuples. But if you look at the actual implementations of the systems like PostgreSQL and so on, they all have an order. In fact, you can even sort the contents of a table with an order by statement. So for this reason, what you actually have in practice is more like a list of tuple implementation. If you are a mathematician and you really want the purest form of a relational model, then that would be a set. Okay, does it make sense? So what we call a tuple, either you know that this is what a tuple is, or you don't care and you just call it a record. You can also say a set of records if you prefer to say a set of records, but this is basically, these are the rows. Now, why did I say a table is a collection? Because now we can say a table is a collection of rows. And a collection can be with set, bag, or list semantics. Who is following me? Okay, very good. So I haven't scared you yet. Now, if I do a little bit of math, what is a tuple here? It's basically a function that assigns the attributes to the values. For example, let's take this one, this one, second one. I can write it down mathematically like this as a partial function. Why partial? Because it only maps 4 attributes, but the set of possible attributes would be very large. It's any string, right? But it's partial. So it assigns the value 2 to PAD, Ramanujan to last, Srinivasa to first, and India to the country. For the notations, it's not official, right? But I tend to use S for strings and V for value, but it's not very important. But basically, this is what a tuple is. It assigns a value to attributes. That's a tuple. That's also a tuple. Sound strike? Yeah, that's the same thing. It's just a different syntax, but it's exactly the same thing. This is, look here. Sorry. Yeah. Do you see it's the same thing? This is the mathematical way. This is a syntax. What is it called? Do you know? JSON. This is JSON. So this is a syntactic representation of a tuple, right? We'll come back to that. Okay. But in fact, the database people prefer to view it in that way because that JSON is actually flat, but we'll come back to that. This is the way to visualize it as a row in a table, right? So this is the intuitive display. And a table is just a set of these things. Okay, so now there's a few things, a few constraints that we put on our tables, because if we don't have this constraint, it's not really a table. It looks like a table, but it's not really a table. So if I say, I take a collection of tuples, set, bag, or list, I take a collection of tuples, and I try to assemble them together. Will it work? Sometimes yes, sometimes not. If you think of it, if you really want a table, the tuples that you have in your collection, they should all have the same attributes. Do you agree with this? In the same table, they all have the same attribute. So this here fulfills the criterion that's called relational integrity. I call it relational integrity. It means that all the tuples that I have in my collection, they all have the same attributes. The fancy word for that is support, the partial function. They all have the same attributes. So this is the first checkbox. There's 3 in total. That's the first check. It has relational integrity. For this reason, I can actually compact it to this, right? Because it's the same attributes every time, so I'm not going to repeat them. So I just put it like this. And this is a relational table. This is an example where relational integrity is broken. It's not respected. Do you see what's going on here? There is, in the second row, the tuple doesn't have any name. In the third row, it doesn't have any value for physicists, plus it has an extra value for country. That breaks relational integrity. That's not a table, right? Who agreed that's not a table? Right. So that's not a table because it breaks the first rule. So this is rule 1, relational integrity, the tuples have the same attributes. Then we have rule 2. Rule 2 is called atomic integrity. Atomic integrity has to do with what we put in the cells. What I can put in the cells are strings, dates, booleans, numbers, anything that's called by database people atomic. It's best to understand what is meant with atomic with a counterexample of what is not atomic. And that is a counterexample. Because I put a table, you see here, this is a table in a table. I like to compare it with the Inception movie. A dream in a dream in a dream. You can have a table in a table in a table in a table. It's not allowed in the good old world of relational database management systems. That breaks atomic integrity. You cannot have structures inside the cells. So here it's broken. This is rule number 2, atomic integrity. Then there is a third rule that's called domain integrity. Domain integrity basically says that the tuples always have, for a specific attribute, the same type of value. So you're able to assign types to the columns, to the attributes, such that all the values in there have that type. In that case, it has domain integrity because I'm able here to say these are strings, these are strings, these are booleans, these are integers. So this has domain integrity. A counterexample would be this. Here I can't because here I have a number and here I have a boolean. Right. So of course, you could always tell me, I mean, if you're a mathematician, you will tell me that then you can just put the set of everything in there and that's it, right? It has domain integrity. That's not how it works. You really need to have these kind of domains here that are actually meaningful for a database person. Okay, so here it's broken. Here there's also a 42 that is in the year. So this is broken. This is rule number 3. If we put them together, we have domain integrity, relational integrity, and atomic integrity. So no nested structures, all tuples have the same attributes, and within the same attributes, the value are of the same type. The intersection of these 3 gives you the beautiful world of SQL and relational database management systems of the 70s, the intersection of the 3. Then you have a relational table. Why do I like to present it like this? Because in this course, we are going to break all of the 3 rules, the 3 of them. Yes?
Oh, I was wondering if I could just ask, for atomic integrity, how do we enforce that? Like mathematically, how do we describe that we don't have nestings of tables and tables? Do we also like sort of have a strict sort of data type enforcement like with domain integrity or?
So in practice, you can enforce it by saying that the domains must be atomic, right? Now you can start a philosophical debate because in fact, if you interact, so I'm a data scientist, right? If you interact with computer scientists and let's say high school teachers who teach computer science, now it's taught in high school or even in the bachelor's degree, typically a string of characters, a string is not going to be considered atomic. If you think of it in Java, a string is a class. String is a class, a string is an object. It's not like int or boolean and so on that are actually primitive values. So you could start a whole philosophical debate on what is atomic and what is not atomic, right? It started in ancient Greece, you know, thousands of years ago. So if you want to be rigorous mathematically, it does require some sort of standardization or agreements on what is atomic and not atomic. Now, I'm not teaching a mathematics class, so I don't need to give a formal definition. In practice, when we say non-atomic, it's defined negatively. What we really mean with non-atomic is tables, objects, arrays, you know, all kinds of more elaborate structures, but everything like a string, a number of dates, and so on, these are all considered atomic, right? So I would say in order to answer your question, we basically define extensively what is atomic and what is not. I basically can give you a close list of the domains of what is atomic, everything that's not in the list that's not atomic. You could view it in this way. We'll see in a few weeks that the types you can have are actually pretty standard. It's always the same ones. So it means that the question is more simple than it actually looks. Okay? So really think non-atomic means you have a table in a table, you have an object in a table, an array in a table. That is non-atomic and that's breaking the first normal form. Right? I'll come back to it so many times, we'll have more opportunities. Did I answer your question? Awesome. Okay. So now the beauty is that now we can break the rule. So in the whole course, I'm going to break these rules and we are going to venture out there, out there, out there, out there, out there, and even out there. So this is the world of NoSQL, which means not only SQL, but not today. We'll have enough time during the semester to actually do this. This is the reason why I prefer to give that second definition of the table, because it allows us to basically drop these 3 rules. Okay. It's approaching the end of today, but I'll just continue tomorrow. So let's look at the intersection again. At the intersection, we have tables, the 3 rules are fulfilled, and we have a beautiful way of manipulating these tables that fulfill the 3 rules that's called a relational algebra. You can, just like numbers or matrices or whatever, we just do it with tables. we can actually have some sort of classification of the sort of things that you can do. You can do the union of two tables, the intersection, the subtraction. You can filter or project tables. You can rename the columns, rename the table. You can group or sort a table. I call them shuffling. You'll see why in the lecture. Or you can join tables. You can take two tables that you bring together in order to join them. The tax office does that with the list of people and the list of tax declarations. That's an example. But let's go a little bit through them just to give you an intuition. And again, that's very high level. You can give complex mathematical definitions of that. You can actually do this in the bachelor lectures, but here is just a visual. This is a selection. What is a selection? It means that I pick certain rows and not some others. Imagine that, for example, I pick these two. The selection criterion could be PID is at least 5. Right? If it's at least 5, then these two survive, and I get this table right here. This is a selection. By the way, it's the sort of things you can do in Excel, right? Take a table, you activate the data filter, and then you check and select values, and that does exactly this, right? That's called the selection. The second one is called a projection. It's the same thing, but on the columns. In a projection, you say, I want to keep these two columns. In Excel, you would hide this column and hide that column. And then you get this table. That's called a projection. Okay. Grouping is when you want to aggregate things. It's very powerful. Imagine you're the statistical office of Switzerland and you want to compute aggregated data over the country by canton. Imagine that these are the cantons, foo bar and foo bar, and you want to aggregate them. So foo, for example, in green, 19 plus 4 plus 46, you aggregate it as a single value. That's called grouping. Okay, very, very useful in databases. I'm going to stop here just to not overload you. I think who survived today this thing? Not too complicated yet, right? Okay. So I'll continue this tomorrow. I will talk to you a little bit about normal forms tomorrow. That's the more scary part of it all. But you will see that you won't have to worry too much about the normal forms. Thank you very much for attending the course today. I'll see you tomorrow in this lecture hall over here at 9:15 a.m. Thank you.